So this is work done with my collaborators in Turin, which is Marco Billo, Maria Frau and Alberto Lerda, and my student Sujay Mahato at IMC. It's based on these two papers. I'll mostly focus on just the work done in the first paper. So I'll give you a brief outline of the talk first. I'll first review what Gukov-Witten surface defects are in the context of n equals 4 Yang-Mills theory. So almost a third of the talk will be this review. We'll try to review the properties of the defects that we hope to describe using string theory. And then we'll give you the main setup. So the goal of the project is to realize these surface defects of Yang-Mills theory in a sort of string theoretic setting. So the setup will be this fractional Branes on orbifold backgrounds. This is not a new setup. This was first proposed by Kanno-Tachikawa back in 2010, but we'll sort of see what was left over from that proposal there. Then sort of half the talk will be sort of an overview of the main idea at this point. And then after I try to convey the main idea of how we hope to realize the properties of surface operators in string theory, I will try to go into the details of how exactly one does this by computing some string correlators on the worldsheet. So I hope the plan is clear. So I'll first start with the review of surface defects. Of course, please stop me if you have any questions. All right, so surface defects are codimension 2 defects in case studies. And these sort of natural high-dimensional generalizations of Wilson and Etu flying defects. And we'll just focus on such defects in n equals 4 Yang-Mills in 4 dimensions. So codimension 2 means to be like surfaces in d equals 4. And for our purposes, for this talk, we'll just focus on 2 planes inside R4. So I'll work with Euclidean space. And the defects will be some 2 planes inside R4 as shown here. These were introduced by Gukov-Witten back in 2006 as monodromy defects. So let me try to explain what that means. So in this figure, I've sort of shown the plane that is transverse to the defect. So Z, so if you remember here, Z was the sort of 2 plane that was transverse to the defect. So I've just now drawn it as a real 2 plane. And it's a defect because, so it's like a disorder operator in the sense that as you approach the defect, Gukov-Witten claimed that the defect is characterized by singular behavior form, the gauge field, and one of the 3 complex scalars of n equals 4. So A goes like alpha d theta, and phi, one of the scalars, goes like 1 by z. So alpha, beta, gamma are these points, some sets of parameters I'll describe in a moment. But I hope this point is clear that it's a monodromy defect because if I now compute the holonomy of A around this point, so this red dot is a defect. So if you compute the holonomy of A as in a closed loop around this defect, you'll find that it's non-zero and is characterized by alpha. Okay. So the defect is essentially characterized by these singular profiles for the gauge field and the scale. So let me try to explain a little bit in more detail what these alpha, beta, gamma are. So we'll always focus on UN gauge theories. So A is some Lie algebra valued 1 form. And what we are saying is that A looks like d theta with a coefficient matrix that looks like so. And this is what we call a generic defect. So there are some parameters alpha naught to alpha m minus 1. So m parameters here. So these are all block diagonal identities of n naught by n naught and so on. So A looks like so, and phi looks like exactly the same form. This matrix form is exactly the same block diagonals appear here. But the parameters are, alpha naught to alpha m minus 1, beta, gamma, again, take m values each. So as you can see, at the location of the defect, the non-trivial profiles for the gauge field and the scalar breaks the gauge group to a subgroup. And the subgroup is precisely this un naught, un1, and so on up to un n minus 1. So this gives you a generic breaking. These could be any integers. All right, so I hope it's clear what the profile of the four-dimensional fields look like near the location of the defect. So one can just check by using the supersymmetric variations in Poincare space, I mean in Euclidean space, that these profiles preserve half of both the Poincare as well as the conformal supersymmetrics. So it's really a half BPS defect. And the defect is characterized by sort of two sets of parameters. The first, just a partition of n, these n naught to n minus 1, that tells you how the gauge group is broken, like so. And in addition, you have these parameters, alpha, beta, and gamma, that specify the singular profiles of the gauge field instances. So these are sort of defining data of the surface defect, and it sort of is part of the definition. So because we are in 4 dimensions, 4 dimension 2 also means dimension 2, as we've just seen. So in addition to these 3 parameters, when you do these path integrals over configurations that include these defects, you're allowed to turn on a 2-dimensional theta term along the defect. So this is unlike those singular profiles. It's just something you're allowed to do in the path integral. You can just include these extra m parameters eta for each of the u1s in this unbroken gauge group at the defect. So I hope this point is clear that the Gukov-Witten defect is characterized by discrete parameters n naught to n minus 1, some integers, a partition of n, and in addition by sort of 4 sets of real continuous parameters. Okay. So what we hope to do in our project is to understand sort of, or to give a string theoretic origin for these parameters by realizing this surface defect in string theory. So we want to know what these parameters would naturally be in string theory. Are there any questions at this point? Okay, if not, let me go on. So there's one other property of the surface operators that is interesting, which is the fact that because we're in n equals 4, there's a non-perturbative duality group, which is the modular group SL2Z. And Gukov-Witten in their paper show that these parameters, alpha, beta, gamma, eta, they transform naturally under this SL2Z action. So in particular, alpha and eta will get exchanged under this S action. So here I've given you how they transform under a generic group element. But if you had, if you just took like MQ to be 0 and NP to be 1 minus 1, you'll see that alpha and eta are exchanged, and beta and gamma just get rescaled by this factor. So tau is the complexified gauge coupling of 4-dimensional gauge. So this would be a check. So if you do realize this surface operator or surface defect in string theory, then it better be that whatever however you realize your parameters, they satisfy this property under estimate. So this is going to be a check for us at the end. So as I said, the goal is to embed this defect in string theory. And by this, we mean that derivation of the profiles of the gauge field and the scalar using purely worldsheet computation. So you should think of this in some sense in the same sort of geometric engineering of some particular gauge theory object in string theory. And what we'll do is to use fractional D3 branes in a particular orbifold background of type 2 string. And as I said, at the end, we will check our proposal by showing that our proposal is consistent with the S-duality properties of the parameters. Are there any quick questions?
Hi, Sujay. Just a quick question.
Yeah.
So this 2-dimensional theta term that you turned on, just to remind that this integral, like this theta term, this lives on the defect itself or the plane orthogonal to that?
No, it lives along the defect. So this integral d, it's integral over d. D is the defect.
So d, I see. Okay.
D is the defect.
On the defect itself.
Right.
I see. I see. And as you were saying that these defects, they break this gauge group into this U1 to the U1 N1, U1 N2, and so on.
That's
so
right.
this some of these alphas or betas, these would be equal. So N1 is a number of some equal number of alphas. Is that so?
Thank you for, yeah, exactly. So these alpha naught multipliers an identity matrix of N naught by N naught and so on. Thanks.
Okay. Thanks.
Yeah. Any other questions? Okay. So if not, let me go on. So let me describe the setup for you. So the setup was described, as I said, by Kanno-Tachikawa about 10 years ago. So what they did was to consider sort of these same Ni stacks of fractional D3 branes on this particular string theory background. So usually, if you recall the old Douglas and Moore constructions of fractional branes, the D branes were completely transverse to the orbifold. But here, what we are going to do is to, as this picture shows, the blue-green directions is the D3 brane world volume. So the two of the directions of the D3 branes will be along the orbifold, and two will be transverse. So your defect will be along these parallel directions, and these perpendicular directions, as I've denoted it, are along the D brane, but also along the orbifold. So this will be this K perp. I denote sort of momenta and so on that transfers to the defect. So we'll see that the defect will be along this first complex. Okay, so the orbifold will be along these 2 and 3 directions, and our D branes will be along 1 and 2 directions. Okay. This was the setup that Kanno and Tachikawa did back in 2010. So I hope this point is clear, that there is the D brane is extended partially along the orbifold. That's why the Poincare group along the D brane is sort of broken, and only this 2-dimensional Poincare invariance will be. Okay, so let's try to recall why Kanno-Tachikawa proposed this. So their goal was to compute the instant-on partition function of a 4-dimensional gauge theory in the presence of such a surface defect. And what they did was to consider these fractional D3s and fractional D-1 branes, And what they did was to compute the effective action of open strings with at least one endpoint on the D-1 brane. And this is what people usually call the moduli action. So what they found was that the moduli action for such a D brane, which extends along the orbifold, is an orbifold of the usual ADHM moduli action. And then they use this to sort of compute the instant partition function in the presence of a defect. So for lower supersymmetric n equals 2 examples and so on, it has been shown that this configuration indeed can be deformed to some other configuration that realizes defects like flavor defects and so on. And this was shown by this paper by Jiang and Microsoft, that in fact one can deform one configuration into another. So it was pretty clear that this configuration had something to do with surface defects, but it sort of what was left out was to understand where these defect parameters are in this orbifold background. Okay, so I hope this point is clear. The orbifold background is all new, but what was unclear was the origin of these alpha, beta, gamma, etas that I mentioned earlier in this picture. Okay. So what we're going to do is to take this picture seriously. So we're going to assume that Kanno-Tachikawa's proposal is correct, and we can ask, now in what sense does it describe? So suppose you didn't consider D instant terms. Suppose it just had a fractional D3s on the orbifold. This is supposed to describe a defect. So you can ask, in what sense is this surface defect? And what we'll show is that we can just recover the profiles that I just described earlier for the gauge field and the scalars using this, in this orbifold background, using conventional string perturbation theory. Okay. So these profiles for the gauge field and for the open string fields indicate that there should be some source or one-point function for these open string fields. So let me try to explain this point, because this one is going to be central to what we do later. So suppose there was a classical source for the open string field that I denote by phi open generically. Then you see, if it's a massless field, then if there's a source, the classical equation of motion would look like so. Box phi would go like the source. And if the source, say, is given in momentum space, then we can reconstruct the profile by just inverting this. So we can just use the, solve the equation in momentum space and do the inverse Fourier transform to find the profile. Okay. So what we think is happening is that the orbifold is sort of inducing, the presence of the orbifold is inducing a source for the open string fields. Right? And once we have a source, then naturally that will be led to some profiles for the open string fields. So our first goal will be to understand the nature of this source. Okay? So is this point clear? That if the orbifold is going to play a role in realizing the defect, that there must be some source for the open string fields. Okay, so right. So what is the source? What is the origin of the source? So as I said, let's recall our setup. We have open strings between fractional D3 branes on this orbifold background, and since this defect is specifically realized by the orbifold, it must be that there must be some states that are particular to the orbifold that must be responsible for the source, and the natural candidates are these twisted sector closed string states. So what we're going to do, sorry, is there a question? Okay, so what we will do is to turn on constant background values for some twisted scalar fields in the orbifold, and then show that indeed it generates a source for open string sectors. Okay. So in particular, what we will do is to compute this disk diagram. Okay, so what we will do is to turn on background value for this closed string field, which I denote mu b, and compute this open closed correlator. So note that this closed string field does not have any momentum modes. It's just a constant wave that I give to this field. And then we'll see that with this constant wave, this correlator is non-zero. And we'll interpret this to be the source that I mentioned earlier in momentum space. And once we compute this correlator, I'll just do the Fourier transform to derive the profile for the open string field. And what we'll see is that the profiles are exactly what we saw at the beginning for the Gukov-Witten defect. And so these background values for certain closed string scalars are identified, will be identified with the alpha, beta, gamma, eta parameters of the defect. Okay. So this is going to be the sort of basic idea. Yeah. Questions? Okay. Sorry, if every noise, I think there's a question, and I'm sorry if I interrupt you. Okay, so let me just point out that this is not a sort of radically new idea. A similar idea was used by many of my co-collaborators in the past. So for instance, the boundary state formalism was shown to be very useful in obtaining the leading correction to the p-brane profile in supergravity when you consider the PP brane as a soliton in supergravity. In the same way, which is much more close to this work, my collaborators showed back in 2002 that the classical gauge instanton profile in D equals 4 can be derived in exactly the same way by considering just D3, D-1 systems and computing the profile for the D3 gauge field. And all the examples what they share is the common idea that that there is some worldsheet configuration that acts as a source for either an open string or a closed string field. And then by just using the simple idea that I said from classical field theory that a source leads to a profile, one can just do a Fourier transform and compute the string profile. So in this way, just so happens that for us, the relevant worldsheet is this disk I mentioned, a disk with a closed string twisted sector field inside. Okay. So schematically, what we need to compute is this particular open closed correlator. And what we will need is what we need are the following. First of all, we need the spectrum of closed string states of the orbifold. This is well known for almost 30 years now. So I'll just review this in detail, especially the twisted sectors that we will need. Once we have that, the new information we need is the boundary state that describes this particular D3 brane, partially extended along the orbifold. And lastly, what we need is the spectrum of open strings again for these funny D branes, and this is going to be new. Even the boundary set for the Z2 orbifold was already known earlier, but for the ZN case, we do it from a second paper. And once we have this information, then it's just a standard perturbation theory. Okay, so now what I'll do is to just systematically work through each of these three things: the closed-string spectrum, the boundary state. I'll be quite brief here, and then the open-string spectrum. Okay, so let's recall some old facts. So for the whole of the talk, I'll just work on the Z2 orbifold. So what that means, if you recall, is that we will only describe the simplest defect where the partition is just N0 and N1. But the basic idea is exactly the same for the ZM orbifold as well, and I'll make a few comments about Z. Okay, so let's focus on a Z2 orbifold of this ALE space. Our first goal is just recall the vertex operators for the twist sector scalars, and all of what I'm going to do in the next 5 minutes is mentioned in half a page of Douglas and Moore. So if you want, you can look at that, but I'll take some time to go through this. Okay, so if you didn't have the orbifold, the isometric group of the space is just SO4, which I'll write as SU2 times SU2. And the orbifold group is going to be this discrete group Z2 or ZM is going to be embedded in one of these two SU2s. So the ALE space has SU2 as the isometric group. So what we'll find is that all physical states of the orbifold, before you introduce the D-planes, will all be described by representations of SU2. Okay. So let's see how to write vertex operators. In the twisted sector, in the bosonic sector, the scalars have this kind of antiperiodic conditions as you go around the closed string. So the ground state is not the usual NS vacuum, but instead is a twist operator, is generated by a twist operator with dimension 1/4. Similarly, for the fermions, what happens is that because of the presence of these extra signs, in the NS sector, we will have non-trivial zero modes in the fermionic sector in these two directions. Psi 2 and Psi 3 will have zero modes, whereas in the Ramon sector, only complex directions 1, 4, and 5 will have zero modes. Okay. So let me just summarize this very quickly. The NS sector vertex operators will just, NS and Ramon sector vertex operators will just split up into each sector. So bosons, fermions, some momentum modes, which we will ignore. We'll just set momentum modes to 0, and we'll just consider constant background values. And lastly, we'll have some super ghosts. Okay. And for NS sector, we'll choose -1 picture, and for the Ramon sector, we'll choose -half or -3/2. So in case you are familiar with this, it'll be a little bit boring. And if you're not familiar with this, I think it'll be too fast. So I'm sorry to both to all the audience members. I'm sorry. But in any case, let me just quickly go through the closed string vertex operators. So I'm just listing the vertex operators in the twisted sectors. So all of these operators in the NS sector will have these twist field, which generates the vacuum in the sector. It has a dimension 1/4. So e to the -5, the super ghost has dimension 1/2. And as I said, the fermions will contribute non-trivial zero modes. So you'll have the spin field in these 2 and 3 complex dimensions. We can check that the dimensions operator is 1. And similarly, I can, so you see, your NS sector vertex operator on the left moving side is a spinner of SO4 or of SU2. Okay? So it's an SO4 spinner. So if you put the left and right moving sectors together, you'll have to form, you form a tensor product of 2 spin-half representations. And what you get is a triplet and a singlet. So that's what I've written here. The triplet is used with the left and right moves are combined with the Pauli matrices, and the singlet is just used from the epsilon. Okay. As expected, they transform under the unbroken SU2 plus representations of the isometry. So these 4 scalars will play an important role. So these are the 4 scalars that appear in the NS set. Okay. Similarly, in the Ramon sector, we'll have the left movers will be spinners of the SO6 directions, which are the unorbifolded directions of the background. And I won't go into the details. I'll just give you the answer. The answers are written here at the end of the page. The important thing to keep in mind is that I'm going to use this asymmetric picture to write the vertex operator, so that these will be vertex operators for the potentials. Okay, so I'll have one scalar and one two form in the RR twisted set. Okay, so that's the spectrum of the twisted sectors in the of closed string. Okay, next let's add D-branes. So again, I'll only consider fractional D-branes in this setup. And the only thing to keep in mind is that from the earlier case is that the D-brane is partially extended along the orb. Okay. So the first thing that happens is that whatever we discussed earlier, all these scalars, all these NS and Raman fields we discussed, will now no longer be treated as the representations of the SU2, because SU2 is not broken by the presence of the D-brane. See, the D-brane breaks the isometry to SO2 times SO2 times SO2, as opposed to an SU2 that was here. So instead of talking about triplets, I'll just consider 4 scalars here, which I denote B, B prime, and B plus minus, which is exactly the same, guys. I just no longer use the triplet notation because SE2 is broken after all by the D. So I have 4 scalars from the NS sector and 2 scalars from the Raman sector. Okay. Out of this 2 form, the ones along the 1-2 directions will just generate a scalar as far as the unbroken isometry is concerned. So at the end of the day, I have 6 closed string scalar fields in the twisted sectors, and what I want to do is to turn on webs for all of these guys. And my hope is that 4 combinations of these will turn out to be parameters that I'm looking for. Okay. Are there any questions at this point? Okay. So once I list the closed string scalars, what I want to understand is now how are they affected by the presence of the D-brane. Now, the coupling of the closed string fields to the D-brane is specified by what is called the boundary state. And you know, it's by now it's well established how to construct boundary states in these simple orbifolded backgrounds. I just have one slide on this. I just want to summarize the main points. So these D-branes in these orbifolded backgrounds, fractional branes, have an untwisted part and a twisted part. So this U tells you how it couples to the untwisted fields like the supergravity multiplets and so on. And these this T set, the twisted sector part of the boundary set, tells you how it couples to the twisted sector scalars in the twisted sector closed string fields. So we are interested in this part of the boundary set. In fact, our excitations are just the spin fields, are just the ground states. So all we really need is the ground state part of the boundaries of the boundary state. And what that tells you is how the closed string fields are reflected by the presence of the boundary. This is again well known that in the presence of the boundary, the left and right moving sectors of the closed string fields are related because of the presence of the boundary, and the boundary state exactly tells you how they are related. Okay? So these are what I call reflection rules, and it's just something that tells you how the left and right movers are related by the presence of this particular boundary state. So I'm not giving you the details of the boundary set, it's there in our paper, but all we need is this, all we need for the computation of the correlator is just this reflection. Okay? Okay, so now we are left with the most interesting part, which is the open string spectrum.
Hello. Sorry, Sujay. Is there some simple way of differentiating what is a boundary state corresponding to fractional D-branes versus full D-branes? Is there?
Yeah, so here in this case, there will be representations of the orbifold group.
Okay. So is it that the full D-branes could be like trivial representations? Or,
yeah, but that these fractional branes are going to be labeled by the irreducible representations of the orbifold. So I here will be just 0 and 1 because there are only 2 types of Z2. If I have M, there will be M fundamental D-branes here, out of which you can make other D-branes. Right?
Sorry, I didn't get the last sentence of it. My body is probably covered. Yeah. Can you just repeat what you said at the last sentence? Yes, please.
I'm saying the ith fractional brane is going to be labeled by the ith irreducible representations of Zn in this language.
Okay.
Yeah, I'm sorry. Well, I wrote it here, but I didn't really say it. Maybe I didn't write it either. Yeah, so they're labeled by exactly the orbifold. Is that fine?
Okay. Yeah, I think roughly fine. And
so I'm going to take ni stacks of these ith fractional brane. That's my setup. I'm taking D3 branes of type I and taking ni stacks. Okay, so the new part here is going to be, I mean, up to now it's been fairly standard stuff. But for open strings, so for open strings, the another feature here is the fact that I have open strings on the D branes that propagate along the orbifolded directions. So what happens then is that when you write it, so if you just had the fractional branes transverse to the orbifold, the open strings that are left in the spectrum are invariant combinations of the oscillator modes and the Chan pattern factors. And then you just see, you look at the combined charges of these two under the orbifold action, and you keep those that are invariant. But now, from what I just said, because I have momentum modes along these perpendicular K-perp directions that are along the D brane and also along the orbifold, these factors also have non-trivial orbifold charges. So what happens is that you have to project on a product of oscillators, Chan pattern factors, and momentum factors. Okay, so in particular, instead of plane waves, what I will have are things like cosine or sine functions. And you have to do this to orbifold projection on the combined factor. So for instance, in the Zn case, instead of plane waves, I have to choose these complicated combinations of the usual plane waves. So the orbifold group on this EI will be some omega to the I times I. Okay. So as a result of this, what we find is that unlike the earlier case of branes transverse to the orbifold, no open string state is projected out from the original D3 brane. Okay. So as long as the state carries momentum along the orbifold directions, the state is kept in the theory. But of course, supersymmetry is broken because of the presence of the orbifold and the D brane. So what happens is that you have an additional two-dimensional sector in addition to the four-dimensional sector. Okay? That's what leads to the breaking of supersymmetry. And you can check this by computing the one-loop partition function. And you can show that if you do the partition function for these with these boundary states, you find a 2D sector and a 4D sector. And right, so now we have all the things in place. All we have to do now is write down the open string vertex operators here. We already have the closed string vertex operators. Let's compute the open close coordinates. So and another simplification that happens is that because I only have a single insertion of an open string field on the disk, I only have to bother about, I mean, since I'm interested in this diagram, I'll only consider diagonal Chan pattern factors. So even the extra complications. Okay, so now let's spend a few minutes trying to understand this thing I said about the open strings. So usually in this canonical -1 picture, the string vertex operator for the Yates field looks like so in n equals 4, and the scalars look like that. Okay, so psi mu and psi are worldsheet fermions, phi is the superghost, and e to the ikx are just momentums. Now one could equally well work in the zero picture by acting with the pitch changing operator, and this, it's equivalent way is to work with this operator. Okay, so now instead of this starting point, what I have to do is to work with this starting point. You see, so I've written everything in a complex notation. So these parallel, psi parallel, I mean fermions along this first complex direction, psi perp, I mean fermions along the second complex direction. So second guy is the one that is, along the D brane, but also along the orbifold. You see, here you can see that it is this combination that is invariant on the orbifold because sine is odd and psi perp is odd as well. So together this guy is invariant. Okay, and this guy is of course invariant. And now what we are interested in is to obtain these operators in the zero picture, because all of our closed string vertex operators were in the -1 picture. So since total picture number has to be -2, what I'm interested in is the open string vertex operators in the zero picture. So I'm just going to flash them to you so that to show that we have it explicitly. So this is the operator that we have in the zero picture. And again, I'm using complex notation. So by these A1, A2, I mean these A1 and A2 here in the next line. So the gauge field has, so this is the one along the defect, and this 2 bar are perpendicular to the defect. Okay, so now we have everything in place. I have all, and similarly we can do it for the scalars and so on, no problem. And again, we find three complex scalars and their complex conjugates that are in the BRST code. Okay, so now we have everything in place. I don't know how much time I have left. I have a lot of time left, but I won't spend too much time on the details. We'll just show you roughly what we do. So this is the correlator to be computed, and the coupling that we're interested in, the source, is just the string amplitude. So I just have to divide by the projective volume. Another way to think about this is instead of doing this, I can just introduce the C ghosts, and this is essentially the volume of the SL2R, which are generated by this conformity vectors of the disk. Okay, so here is a sample computation. This new A2 is the vertex operator for the open string field. These new B is the vertex operator for the singlet closed string scalar that I mentioned previously. This is what it is explicitly, and we just have to compute the correlator, and it's very easy once I use the reflection rules. Once you use it, it's essentially like a disk 3-point function in the open string sector. It's equivalent to that. Okay, and every sector decouples: the superghosts, the bosons, the fermions. They all decouple as expected, and the final answer is very simple. It's just that. Okay, and if you now use this relation and try to find the source, you find that the only non-zero couplings are as follows. So I was very fast to this because I didn't know if people were interested in the details, but it's a standard string perturbation theory. I didn't want to spend too much time there. But the only non-zero couplings are for these two gauge fields, and one along the defect, one perpendicular to the defect, but along the D plane, and this complex, and one of the complex terms. Okay, this is exactly what we would hope for. There is a gauge field and scalar source for them. Okay. And note that all of these sources are proportional to the background values for the closed string field that have to be returned. So B and B plus are the NS sector scalars, and C is the Raman sector scalar. Okay, so we had 6 scalars to start with, 4 and 2, 4 from the NS and 2 from the Raman. Now, rather miraculously, in the Z2 case, we find that none of the open string fields couple to these scalars I call B prime and C prime. So there are exactly 4 scalars in the twisted sectors that couple to the open string fields. So that's extremely nice. And similarly, note that there is a momentum conserving delta function along the defect. This is also something that you'd expect, because the Poincare invariance around there is unknown. So now all that remains is to use these couplings as sources, use the Fourier transform, and read up the profiles.
Sorry, Sujay, what was this kappa 2 and kappa bar 2 and so on?
So these are just complex problems. So this is something like K3 plus IK4, and K1 is K1 plus IK2. Sorry about that. Yeah, that's it. Yeah.
Yeah.
Okay, so now, as I said earlier, the open string profile is just the Fourier transform of the source. And you see there is an extremely trivial computation. The source looks like a complex momentum times delta function. So the delta function along the parallel directions immediately reduces it to a integral over the K perp, just the plane transverse to the defect. And this is just the derivative of the Green's function in 2D, and I get the simple pole that I'm looking for. Okay? So this is the sort of rough analysis. There are concepts and so on, but I hope this idea is clear. The string computation is pretty standard. 3 and 4 point functions. I mean 3-point functions on a disk. That gives me these couplings, and once I have these couplings, the profile is just the Fourier transform. Okay, so I put all the constants back in, and this is what I find for the component of the gauge field transverse of the defect. It's 1 by Z bar, and now I just put in find the complex conjugate result, and I find that the profile is precisely what we had for the Gukov-Witten defect. b times d theta. So d theta is precisely this angular coordinate in the plane transverse to the defect, but along the d brane. Okay, and the same computation goes through for the scalar profiles. I get the simple pole that characterizes the Gukov-Witten defect. Okay, and now we had n0 branes of type 0 and n1 branes of type 1 in the Z2 orbifold. And these things don't depend on, so it just depends on the fractional brane with this -1 to the I label. So it's just this matrix form, and this is exactly what we'd expect for the Gukov-Witten defect of type n0 n1. So essentially, as I'll show you, B is like alpha, and B plus is like the beta plus I gamma. Okay. So remember, all of these are just for the NS sector scalars. Let's see what happens for the Raman sector scalars. So the Raman sector couple only to the gauge field along the defect. And at first glance, it's a bit weird because it looks to be 0. Because you see, I have a delta function for K parallel. And then I have this K1 here, or kappa 1 here. So it seems as if it should be 0. And indeed, there is no profile for A1. As a profile, this shows that there is no profile for A parallel. But if you think a little bit, you'll find that if you put back in the polarizations of the gauge fields, which we did not do so far, if you put in the polarizations, what it's giving me, in fact, is the field strength. So you see, if you had a constant field strength turned on the D brane, then you find that this interaction is non-zero. So in fact, what it is telling me is that this Raman sector coupling is in fact showing me a coupling on the world volume of the D brane between the Raman sector scalar C and the gauge field on the D brane. And if you do this Fourier transform carefully, you'll find that it localizes along the defect. So all these factors and so on are such that the Fourier transform precisely gives you an interaction that is localized on the defect. Okay, and that is precisely what one was hoping to find for this theta term, right? The theta term is something you added in the path integral, the Gukov-Witten added in the path integral, where integration was only along the defect directions and not along the full 4 dimensions. Okay. So this is what I've written here, and eta is just the web of the background value for the Raman scale. So at the end of the day, this is what we have, that we are able to reproduce using basic disk amplitudes and so on, and some basic understanding of classical sources and profiles. We are able to identify all the parameters of the 4-dimensional, of the defect of the 4-dimensional theory in terms of the background values of the NS, NS, and Raman scalars. And in the Z2 case, the nice thing is that out of the 6 scalars, exactly 4 scalars coupled, and that's what it is. Okay. Okay. Are there any questions at this point? Because now I'll do something else. So, okay. So now we said at the very beginning, we have to check that what we have is consistent with the known S-duality transformations of alpha, beta, gamma, and delta that Gukov-Witten proposed. Had shown. And here we use the fact that if you blow up this ALE space, sorry, if you blow up this orbifold, what you get is a smooth ALE space. Okay, this is well known from the early 90s by work of Trondheimer and so on. And what we have to do, therefore, is to identify our closed string twisted sector scalars with fields in type 2B supergravity on an ALE space, because the transformations of the supergravity fields under S-duality is well known. And so what we find is that the NS-NS singlet B and the Raman-Raman scalar C are just nothing but the same moduli obtained by integrating the B and C fields over the cycle of the Z2 orbifold. So when you blow up this space, there's a non-vanishing P1 there in the ALE space, and the integrals of these B and C, Raman-Raman and NS-NS to 2 forms over the space are identified with the moduli of the supergravity theory, and they are identified with the B and C scalars that we have in the orbifold. So by just composing the map, we find that alpha, beta, alpha and eta are nothing but these integrals up to these sign factors. And B and C transform as a doublet under the SL2Z S-duality of type 2B string theory. And it's well known that if you realize n equals 4 using the D3 brane, then the type 2B of n equals 4 is exactly the type 2B of the parent supergravity theory. And we find that the alpha eta exactly transform like so. So we have sort of checked that the proposal for alpha and eta being background webs of these B and C is consistent with S-duality. In exactly the same way, the other NS scalars, B plus minus, are identified with complex structure moduli of the Airy space. So the metric moduli and the string plane metric transforms like so under S-duality. And this is exactly how beta gamma should transform from the gauge theory analysis. So overall, we have a proposal that is totally consistent with what the gauge theory expectations are. So in some sense, it's fair to say that we've sort of completed what Kanno-Tachikawa proposed back in 2010, that there's fractional branes on this orbifold realize the defect. Okay, so now let me make some few comments about the generic defect. So we have these partition N0 to Nm. So these are the types of fractional branes we have to take in an orbifold. And we again identify these with the webs of various sector fields of the closed string background. And conceptually, things go through exactly as before. But technically, it's much more complicated now. The sectors are no longer excited states, but we have to work with oscillators and so on. But we do all that in the second paper. And secondly, the open string excitations are vertex operators much more complicated. It's not sine cos, but some more complicated combinations of plane waves that I showed earlier. And the identification is not exactly alpha equals B, but alpha is this sort of complicated trigonometric combination of the web. So BS here is the background value for the singlet field again in the 8th twisted sector. And this, I labels the irreducible representation, if you remember, for fractional branes, and A labels the conjugacy classes. So, the closed sectors are in conjugacy classes and the fractional branes are in the irreps. And, you can imagine that this is the kind of change of basis that usually relates to these two things. So this is our result, and similar expressions hold for the beta, gamma, eta parameters. That's all of that. Also, I should say that in the Zm case, the B prime and C prime scalars also couple to the open string fields. So in principle, one could consider more general defects. But if we want to match with Gukov-Witten defects, then we set B prime C prime to 0, because otherwise the S-duality transformations do not match. So that's something that we also comment on in the paper. But the basic story is the same for Zm. Okay, so these are my final remarks. I've repeated it many times. The basic result is that we've recovered the singular profiles of the fields in the gauge theory using worldsheet. Correlators, questions about defects now in a sort of B-brane framework. So you could ask questions that might not have been obvious in the gauge theory context that you can now ask using B-branes. You can consider intersections of branes, whatever, consider more general defects. So there's a lot to explain. I'll stop here. Thanks.
Well, let's thank Sujay for that wonderful talk. If anyone has any questions, you can go ahead and ask the speaker. If anyone has any questions, you can ask the speaker.
Okay. It's fine.
Okay, so
All right.
if there are no questions, then let's thank Sujay once again. And we'll see you guys next time.
Sure.
Thanks, Sujay.
Sure.